998, 999, 1,000. Oh, hello there. How are you? Whew. Just caught me in the middle of my workout. Whew. Thanks for stopping by. I'm hoping that you're doing a good job of graphing those sinusoidal functions. I think we're probably ready for the next step where we're going to start sort of doing the opposite. We're going to have graphs of sine and cosine curves, and we're going to come up with the equation. So that's the next step. So I've got a few examples to go through with you. They're online as well if you want to take a look at them there. And all right, let's get started. Come on.
So I'm going to work on some examples with you on working with sinusoidal functions, in particular how to find the equation of a sine or cosine function given the graph. So these examples are on our course webpage. If you'd like to follow along, you could have that sheet in front of you, but I'm also going to record all my notes here too, so you won't have to worry about keeping up. You can always look at this again later on. So just as a quick warm-up, a little bit of a review, let's take a look at sketching a graph of, in this case, a cosine function given its equation. So I have to be able to recognize a few things. First of all, I see right away that the 4 gives me the amplitude of that graph, or amp for short. 8 gives me the equation of the axis, so the axis is at y equals 8. And finally, 5, instead of having a period of 360, this graph is going to have a period of 360 divided by 5, which is 72. Once we know that information, also need to take into account the fact that this is a negative here, meaning the cosine function is going to be upside down from what we normally would expect. I can draw a sketch of what this graph looks like. Okay, there's my x-axis, my y-axis. Okay, so there's an axis at 8. So I'd like to start with that. With an amplitude of 4 means we go 4 above 8 to 12 and 4 below 8 to 4. Of course, there's our 0 right there. Now this graph is cosine, but it's upside down. So normally cosine starts at its maximum and goes down, but since it's been reflected in the x-axis, this graph actually starts at its minimum and goes up. So it's going to do something like that right there. Okay, the period is 72, which means that is 72. Of course, half of 72 is 36. That's now where we have our maximum. Half of 36 is 18, so that's where this point right here is. And then finally, my fifth point that I haven't found yet would be halfway between 36 and 72, or hey, look, every key point is 18 apart, so you can just add 18 to 36, and you get 54. So there we go. There's what that graph looks like. Now, I would like to point out that the graph does continue. We just showed the first cycle. We could keep going as well if we wanted to, and the key points would continue to be 18 units apart. So 72 plus 18 would be 90. So there's your next key point at 90. And it also goes off into the negative land as well, too. So just do keep that in mind. Okay. Okay, so there's our warm-up question. What we're going to work on now is essentially the opposite. Oh, actually, I've said let's verify in Desmos. Let's do that as well very quickly. Okay, so if I go to Desmos and I type in y equals -4 cosine 5x plus 8, I get that right there. Now, remember, that's not quite correct. We need to change ours into degrees. It's in radians right now. And then we also need to consider our scale. So for example, this only had a period of 72, so maybe we just want to go to 100. Okay, that's probably good enough right there. And we can see here's our graph. And you can kind of get an idea that, yeah, okay, it goes down to 4, up to 12, and then a cycle ends there at about 72. So it gives you some idea that you're on the right track. Okay, back to our examples. Example 1, find the equation for the sinusoidal function pictured below. So the first thing to do, I mean, we're working backwards here. So all these things that we found from the equation, amplitude, axis, and period, we now need to determine what numbers will be in the equation based on what we see. So the first thing we might look at is the amplitude of this graph and the axis of this graph. Now I can tell very easily, since the max is 50 and the min is negative 50, the axis is right at y equals 0. Remember, you can also find an axis by taking the max plus the min and dividing by 2, but I can do that in my head here. I can see that that's the halfway point pretty easily. The amplitude is equal to this value, or this distance right here, which is also clearly 50. And it's the same down here. That's 50 as well. So our amplitude is 50. Now, if you can't see the amplitude, you could use the equation max subtract min divided by 2. And that will always give you the height of that wave as well. So there's two ways to do it. One using the formula, and one just by looking at the picture and seeing how big, looking at the graph and seeing how big the waves are. Okay, the last thing I want to take a look at for this graph is what is the period. So I can almost imagine tracing out a cycle here. Okay, this graph starts a cycle at, I'm just going to get these out of the way here, they're kind of bugging me now. This graph starts at 0, goes up, comes back down, and then begins repeating a cycle right there. Now, can I tell where that point is? It looks like I can. 150, 160, 170, 180. So the period is 180. Well, that's different than a period of 360, obviously. So it must be that the number that we horizontally compressed this graph by a half. So that means that this number right here, which was a 5 in this above example, is now going to have to be a 2. The last thing we need to realize too, we know the last number will be 0 instead of 8 because our axis was at 0. And we know that our starting value, I often call it our A value, is going to be 50 instead of 4. The last thing we need to do is look at this graph and realize this graph looks like sine. Sine always starts at its axis and goes up, whereas cosine starts at its maximum and goes down. Just think back to your original sine and cosine graphs. So since this graph starts at its axis and goes up, this is a sine graph. And we're ready to write the equation. Y equals 50 sine 2x, and of course we don't need to write plus 0. That is the equation of that graph right there. Let's try another one. Okay, find the equation of p of x given its graph pictured below. So we'll go through the same process here. Let's look at the axis. Okay, -5 and -1. Now suppose you're having trouble deciding where the axis is. You could simply take -5, add it to -1, and divide by 2, and you will get y equals -3. And sure enough, that's exactly where the axis is, halfway between those values. The amplitude is now the height of each wave, which would be -3. Notice it goes up 2 to -1 and down 2 to -5. Our amplitude is 2. All right, we also need to look at the period. Notice this graph starts at its minimum and goes up, comes back down, and then once it gets to 90, it starts to repeat that pattern. So the period, the length of a cycle here is 90. Okay, now coming up with the equation. Let's start with the easy part. Well, sorry. Let's also think about whether we have sine or cosine here. Notice this graph starts at its minimum and it goes up. Well, neither sine or cosine starts at its minimum, but cosine starts at its maximum and goes down. So it's possible that we could have taken the cosine function and reflected it, flipped it upside down, and we would get this graph here. So this is a cosine function that's been flipped upside down. We know the amplitude is 2, so we know that the equation is going to look something like this. But what about the value right here in front of x? I call that a k value, by the way. When we first introduced transformations, this value right here we referred to as k. The period is 90, so we not 360, so we obviously horizontally compressed it. Now, a lot of you can probably see right away that 90 is a quarter of 360, so our value is going to need to be a 4 right there. And that's true. But there's also this little formula here we can use, and that's that the period of the graph is always equal to 360 divided by your k value. In this case, our period is 90 So 90 equals 360 divided by k. Now that's a pretty easy equation to see that k equals 4, but if you wanted to, for a harder example, you can multiply by k and then divide both sides by 90, and there's your 4 right there. And we'll just plug that in up here. -2 cos 4x minus 3. If you went to sketch this, you would get a period of 90 because you would take 360 divided by 4. You would get an axis at -3 and an amplitude of 2, and you would draw the cosine function upside down. It'll give you this graph right there. I've got one more example for us to work on together. When we first talked about periodic functions, I actually gave you this as an example of a periodic function. This graph shows the day of the year and the amount of moon that is visible in the sky that night. This is for one particular year. Not every year has day 0 at close to 0%. So we're going to find an equation to model this. And our equation is not going to be exact, because what we're going to do is we're going to assume the period is exactly 30 days. In real life, it's not. I believe the period of moon cycle would be 29.5 days, but we'll use 30 for this example. Okay, so our maximum is 100%, of course, and our minimum is 0. That means our axis is halfway at y equals 50. And since we go from 50 to 100 and 50 to 0, that means we also have an amplitude of 50 as well. Okay. Notice again, just like the previous example, this graph starts at its minimum and goes up, which is exactly the opposite of cosine. So I'm going to use the cosine function reflected again. If you're having trouble deciding between sine and cosine, just keep in mind that in my head I know that sine looks like this. It starts at its axis and it goes up. And I know, so that's sine. And I know that cosine looks like this. It starts at its maximum and it goes down. So I'm choosing, I'm thinking about the graph I have. Does it look like sine? Does it start at its maximum and go up? Or does it start at its axis and go up? Or does it start at its maximum and go down, in which case it's a cosine graph? And if it's not one of those, maybe it's one of these graphs reflected. For example, in the graph here, it's cosine upside down, and so we can use the cosine function. It's possible you could have another example where you had the sine function upside down. It starts at its axis, and it goes down instead of up. In fact, one of the assigned questions I'm going to have you do, you're going to need to use that. So we've got a cosine function, amplitude of 50, axis at 50. Now we just need to think about the period, which gives us the k value. The period here is 30 days. And so like I told you, we can use this little formula. 30 equals 360 divided by k. So it's kind of like the k values kind of tells you how much you're going to horizontally compress or stretch the graph by. Okay, well, if 30 equals 360 divided by k, that means 30k equals 360. Divide both sides by 30. 360 divided by 30 gives you 12. Once we've got that, we're able to finally write out this equation. So we have y equals, or let's better yet, well, it's hard to think of good variables here. We're going to use A for amount of moon visible, and I don't know, N or D for day of the year, I guess. Okay, AD equals, let's see, 50, sorry, negative 50, cosine 12D, and then plus 50 as well for our axis. And there's our equation. So there's a negative sign there. Make sure you don't get that. Now, do you need brackets here? You don't technically need them. This is okay. But it's not a bad idea to include them as well. Sorry, those are meant to be brackets I'm drawing in there. And that's still a 12. There we go. Okay. So there we go. There's our equation. Now, we can use that equation to make predictions about how much percentage of the moon you should expect to see every day of the year. So as an example, I've said, what about day 150? So basically, we're saying, okay, let's actually use this equation. So sub in D equals 150. Or calculate A of 150. Which is negative 50 cosine 12 times 150 plus 50. And we use our calculator to do this. Now, depending on what kind of calculator you have, changes how you're going to do this calculation. My calculator, I believe, here is non-DAL. So I'm actually going to start with 12 times 150. Okay, 1800. I take the cosine of that. Okay, which gives me exactly 1. Look at that. I times that by negative 50. And of course, I get negative 50, and I add 50, and I get 0. So on day 150, it's what's called a new moon. We'll see 0 amount of the moon. That may not have been the greatest example to do. Let's pick like an odd day, like, I don't know, day 93. Okay, just like that. And let's see how this works out. So 12 times 93. It's that right there. I take the cosine of that, and notice I get this number here. This is actually irrational, meaning the decimals go on forever. So I times that by negative 50. Okay, and then I add 50. And I get 9.5, about 9.5. So only about 9.5% of the moon will be visible on day 93. Okay, I hope that was helpful for you. I've got a short set of assigned problems that I put online for you. I'm also going to upload this file, so you'll have these examples as well. And please feel free to send me an email if you have any questions. And don't be afraid to, if you want to, post a question right below the YouTube video, and I'll be able to answer it for you, and then everyone will see the answer as well. Okay, thanks, and bye for now.